Hello. This podcast is the second in a two-part series on describing uniformly accelerated motion. In part one, we learned how to describe accelerated motion with words and motion maps. In this podcast, we're going to learn how to use position time graphs and velocity time graphs to explain and describe uniform motion. First, we'll take a look at how we use position time graphs. Here is the position time graph for the dune buggy and the fan cart that we saw in the first podcast. This is the first segment when the fan cart was speeding up. The dune buggy is in green dots and the fan cart is in red dots. Notice the dune buggy has a straight line as a position time graph, which we know that from our previous unit on constant velocity. However, the fan cart's position time graph is not a straight line, it's a curve. And that's because the displacement every half second is getting larger and larger. And when that displacement gets larger and larger, it bends the line and creates a curve. Now, the velocity of the object is simply the slope of the position timeline. Now, when it's constant velocity, we have a straight line and the slope is the same the whole way, which means the speed doesn't change. However, we know with speeding up that the speed's going to get larger and larger, and that shows in the curve as the slope is going to get steeper and steeper. Notice that the curve starts out flat and it keeps getting steeper and steeper. That means the object is getting faster and faster. And we can turn on our tangent line function. And this is just a neat function that we can put over each data point. So here you can see the tangent lines for the dune buggy and for the fan cart. And up here you can see the slope. So the dune buggy is going faster. It is a slope of 0.449 meters per second. The fan cart, only 0.251 meters per second. Now, if we go to the next data point, you can see that the dune buggy's slope is the same, but the fan cart's slope has increased to 0.35. When we go to the next data point, now the fan cart is going a little bit faster than the dune buggy, 0.493, whereas the slope the dune buggy is basically the same, 0.44. If we move on to the next time data point, you can see the fan cart slope is getting even steeper, 0.644, whereas the dune buggy's slope is remaining essentially the same, 0.433. If we move on to the next data point, the fan cart's velocity has increased to 0.767 meters per second, and at 1 second, the fan cart's velocity has increased to 0.842 meters per second. So let's take a look at what this position time graph looks like for slowing down. Okay, when the fan cart was slowing down, here's our position time graph. We can see that the dune buggy in green here is a straight line. That means constant velocity. The displacement every half second is the same. However, with the fan cart, we know that the displacement is getting less and less as time goes on, and that acts to flatten out the line or bend the line down, creating a curve. Now this curve, notice, this curve goes from steeper to flatter. That's different than our speeding up curve, which went from flatter to steeper. And so when you have a curve that goes from steeper to flatter, remember the steepness is an indication of the speed. Well, if it starts out steep, that means it's starting out fast, and if it gets flatter, that means it's getting slower. So this shape, where it flattens out as time goes on, is a position time graph for an object that's slowing down. And we can just go ahead and use our tangent function and take a look at this. So we can see initially the fan cart was going much faster than the dune buggy, 0.722 meters per second versus 0.414 meters per second. If we go to the next data point, fan cart slowed down to 0.642
In our next data point, the fan cart slowed down to 0.526. When we go to the next time point, it slowed down to 0.402. And when we get to the next time data point, it slowed down to 0.295, and it is now going slower than the dune buggy. And at our last data point, it slowed down even more to 0.225 meters per second. So again, this is a position time graph for an object that's slowing down. It's a curve, just like the object that's speeding up, but the curve goes from steeper to flatter, whereas when it's speeding up, it goes from flatter to steeper. So let's go take a look at velocity time graphs. Here, once again, with the green data points is the dune buggy and its constant velocity. So we have a flat line. It's around 0.45 meters per second. Notice in red we have the velocity time data for the fan cart. Notice this is not flat because the velocity is not constant when an object is accelerating, and the velocity is increasing. So we have a velocity line that is moving away from the time axis. So here's a big distinction between constant velocity and accelerated motion. Velocity time graphs for constant velocity have flat lines. Whereas if the object is speeding up, the velocity line is going to be straight and it's going to be moving away from the time axis. It doesn't matter whether it's starting in the positive region or the negative region, the velocity line is going to move away from the time axis as time goes on. Now let's take a look at slowing down. In this figure, we're looking at velocity versus time for the fan cart slowing down. We have our constant velocity example. The green triangles represent the data for the dune buggy, and it's a flat line at about 0.38 or 0.39 meters per second, constant velocity. Of course, we're not going to get a flat line for the fan cart because the velocity is changing. We are going to get a straight line. And in this case, the straight line is going to slope towards the time axis. Remember, down here at velocity equals 0 is the time axis. So whenever an object is slowing down, the velocity line is going to be straight, and it's going to start further away from the time axis and move toward the time axis. That's the opposite of an object that's speeding up. For an object that's speeding up, the velocity line is going to start closer to the time axis and move away from the time axis. It doesn't matter whether you're in the positive region or negative region of the velocity time graph. If an object is slowing down, the line is going to move towards the time axis. This covers the basic characteristics of velocity time graphs for speeding up and slowing down. This also wraps up our two-part series on describing uniform accelerated motion. I hope this helped, and have a good day.